This lesson is all about the TLS 1.2 handshake. As a short recap, the overall objective of a TLS handshake is the construction of a secure channel from an insecure channel between communicating peers such as a client and a server that have never met before. Looking now to the drawing on the left side of this slide, we can see that a TLS 1.2 handshake conceptually goes through 5 stages. The coloring of these stages is reusing the same coloring as used in the previous lessons, where we had an in-depth look at the cryptographic processes taking place within TLS. Having this coloring at hand here hopefully helps to put the individual stages of the handshake into perspective of its intended purpose. The TLS 1.2 handshake starts with a stage where the client and the server agree on a specific TLS version to use and by agreeing on a specific cipher suite to use. Once the TLS version and the cipher suite are agreed by the client and the server, the peers are authenticated. In TLS, the server is always authenticated and the client is only optionally authenticated if explicitly requested to do so by the server. Sandwiched in between the authentication of the server and the authentication of the client is the step where the client and the server agree on a master secret. This master secret within TLS 1.2 is either agreed on via RSA-based encryption of a pre-master secret generated by the client or by the client and the server conducting a Diffie-Hellman key exchange. The reason as to why this stage to agree on a master secret is sandwiched in between the authentication of the server and the authentication of the client will become clear within the next few slides. The handshake then finishes with a finishing stage where the client and the server give each other assurance that both the client and the server each successfully executed the handshake and that both arrived at the same master secret. Let us now have a more detailed look at each of these handshake stages. The handshake starts with a stage where the client and the server agree on a TLS version and a cipher suite, which takes place via the client and the server sending each other hello messages. The hello message of the client, for one, contains an indication of the TLS version that the client wants to use. The client hello message then also contains a list of cipher suites supported by the client and sorted according to its preference, and the last part of the client hello message is a freshly generated 28-byte random number that is an important element into the later derivation of cryptographic key material. Once the server receives the hello message of the client, the server responds with a hello message of its own. For this, the server first chooses the TLS version to use for the session, chooses a cipher suite from the set of cipher suites offered by the client, and freshly generates a 28-byte random number itself. The chosen TLS version, the chosen cipher suite, the 28-byte random number, together with a session ID, is then returned to the client with the server hello message. If a client would want to resume a previous TLS session, the client would send the ID of that previous session with its client hello message. If the server would then find that session ID in its cache, the following handshake could finish early, and the previous session with its master secret would be reused. More on this will follow later on in this course. Once the client and the server agreed on a TLS version and a cipher suite to use, the handshake proceeds into the stages to authenticate the server and to authenticate the client. Within the TLS 1.2 handshake, this authentication of the server and the client does not really happen consecutively, but actually has the stage to agree on the master secret sandwiched in between. It's again important to emphasize that within TLS, the server is always authenticated except if a previous session is resumed. The authentication of the peers within TLS normally takes place via X509 certificates, and for this, the server then sends its X509 certificate to the client. the server actually sends its X509 certificate as part of a chain of X509 certificates, where the server end entity X509 certificate is the first certificate in the chain, and where each X509 certificate following in the chain is the certificate that certifies the certificate immediately preceding it in the chain. This chain of X509 certificates is then sent to the client, and the server then optionally requests the client to also authenticate. Importantly, and we will get back to this on the next slide, the server so far only presented its certificate but didn't actually make use of its private digital signature key yet. This will happen as part of the key exchange later on. The client then receiving the chain of X509 certificates from the server needs to verify this chain of X509 certificates according to the X509 certificate chain validation semantics as defined in RFC 5280. If the verification of the server X509 certificate fails, the client will alert and the TLS session will close. If the verification of the server X509 certificate succeeds, the handshake proceeds. Then, and in case that the server requested also the client to authenticate, the client will respond with its own X509 certificate that the client then also sends as a chain of X509 certificates to the server for verification. Interestingly now, the client immediately follows up with a certificate verify message, which is a message where the client created a digital signature across all of the handshake messages exchanged so far. This digital signature proves to the server that the client is in possession of the private digital signature creation key corresponding to the public digital signature verification key contained in the X509 certificate sent by the client. If then also the server successfully verifies the X509 certificate chain sent by the client and additionally also successfully verifies the digital signature in the client certificate verify message, the peers involved in the TLS connection, or at least the server, are fully authenticated. Sandwiched in between the authentication of the server and the authentication of the client is a stage of the handshake protocol responsible for the agreement of the peers on a master secret taking place by the server and the client sending each other key exchange messages. For the server, there is actually an overlap also with the authentication of the server, as the server is only fully authenticated once the stage for the agreement on the master secret successfully completed. The specific content of the server key exchange message depends on the key exchange specified by the agreed-on cipher suite. If an RSA-based key exchange is specified, then the server doesn't have to send a key exchange message itself, as it's the client that generates a new pre-master secret and encrypts it with the server's public key that the client could fetch from the server X509 certificate. This newly generated and encrypted pre-master secret is then sent to the server within the client key exchange message. If an ECDHE key exchange was specified for the connection, then both the server and the client send each other a key exchange message with both key exchange messages containing a respective Diffie-Hellman half key. From these Diffie-Hellman half keys, both the client and the server can then locally compute the full pre-master secret. Now, importantly, the server key exchange message sent by the server to the client is additionally signed with the server using its private digital signature creation key corresponding to the public digital signature verification key contained in the X509 certificate that the server sent to the client. Only once the client verified the digital signature on the server key exchange message received, the server is fully authenticated. On the other hand, the client key exchange message does not need to be digitally signed, as the client, if requested to authenticate by the server, will immediately follow up its certificate message to the server with the certificate verify message that contains a digital signature created by the client on the handshake message exchanged so far. After the exchange of the server and the client key exchange messages, both the client and the server arrived at a shared pre-master secret. This pre-master secret is then converted into the master secret by both the client and the server making use of the PRF pseudorandom function defined in RFC 5246. Later on, for the secure exchange of application data, this master secret is then expanded into symmetric keys that are used by the client and the server to encrypt and authenticate the application data. The last but very critical stage of the TLS 1.2 handshake is then the stage to properly finish off the handshake. This finish stage of the protocol is critical as it's only with the finish message exchanged that the client and the server get mutual confirmation that both arrived at the same master secret that they will later on use for the secure exchange of application data. Worth to point out here at this point is that these finish messages are actually the first encrypted messages of the TLS connection. The encryption of these finish messages takes place by using the pseudorandom function PRF to derive cryptographic encryption keys from the master secret. To reach the mutual confirmation on the master secret, the finish messages exchanged by the client and the server then contain a value that is again derived with the pseudorandom function PRF from the master secret and a hash of all the handshake messages. If both the client and the server could calculate this value, then the client and the server can assume that both arrived at the same master secret. Additionally, and in case a pre-shared key was used for the connection, it's only with correct finish messages that the client and the server are authenticated, as the use of a pre-shared key means that no certificates have been exchanged. When both peers received correct finish messages, then the TLS handshake protocol finishes and both the client and the server proceed into the exchange of application data secured by cryptographic keys, again derived with the pseudorandom function PRF from the mutually agreed on master secret. With this, it's clear that successfully finishing the handshake means that a secure channel has been constructed between the client and the server, even if the client and the server have never met before. Absolutely amazing, isn't it?